So this is part 3 of the lesson on Gibbs free energy and entropy and enthalpy. So I'm going to write the equation down. Delta G is equal to delta H minus T delta S. This section is going to go beyond what we did in the class meeting this morning and give you 3 more equations for a total of 4 equations that can be used in this unit. All right, but first I wanted to talk about the rubber band. So if you have a balloon at your house or a rubber band, something that can be stretched like this and contract, and actually it needs to be at least this thick. This is a rubber band that came on my mail. So when my mail is delivered, I usually wrap it in a rubber band. So you might find that. All right, so what we're going to do is stretch the rubber band and see if we can assign values for delta G, delta H, and delta S. So first, does the rubber band spontaneously go from this position to that position? Is that a spontaneous thing? And the answer to that, I think we all know, is no. So if that's not spontaneous, stretching the rubber band, all right, stretch here to remind us that we're talking about stretching the rubber band, the stretch would have a positive delta G. It's not spontaneous. Is it endothermic or exothermic? Well, if you do take the rubber band like this, put it against your upper lip. Okay, now stretch it and put it against your upper lip again. This works particularly well with a balloon, but I didn't have a balloon sitting around my house. So cool, that feels warmer. So if it gets warmer, then the delta H would be negative. Okay, so minus something. What I want you to do now is think, what must the delta S be? So this would be, delta S for this rubber band would be, that's negative minus something has to make a positive number. So if this was a positive number, a negative number minus a positive number would always be negative. A negative number minus a negative number could create a positive, so this must be a negative. So the entropy is decreasing as you stretch the balloon, or stretch the rubber band. Now I'm going to call this the snapback. When I hold the balloon like this, or excuse me, the rubber band like this, then the rubber band automatically goes back when I let off the pressure. So if I pull it out, let go, snaps right back. So that is spontaneous. So we would say the snapback has a negative delta G. The enthalpy, well, pull it out like this, put it against your lip, now snap it back, put it against your lip again, and you should notice that it feels cooler. If it feels cooler, that means energy went into the process, so that is an endothermic process, minus. Now what about the entropy? Well, I've got a positive number. If this was a negative number, then that would always be positive, right? So positive minus a minus is plus. But we know it spontaneously went back, so we know delta G has to be negative. If that's the case, then the entropy here has to be positive. So it's getting more disorderly when it snaps back. All right, so that's an example of how these signs apply to something in your everyday life. And just real briefly, why is the entropy decreasing when you stretch it? Think about the rubber band being made of molecules that are like a bowl of spaghetti. So spaghetti that's been cooked, it's all tangled up. But if I took that spaghetti, suppose it's been cool so you can touch it, I take the spaghetti and stretch it like this, then wouldn't the spaghetti parts straighten out? And then when they go back together, they become more jumbled up again. So that's what the molecules are doing, and that's why when you stretch it, the molecules line up a little better, they become less disorderly. But when I put it back together, they jumble up again and become more disorderly. All right, so the equations, there are 4. Delta G is equal to delta H, H minus T delta S. Another equation is this equation for delta H. It equals heat of formation of products minus the heat of formation of reactants. And so we've already done that equation. So you should be now familiar with these two. So here are 2 new equations which are the same as this. You can also calculate delta G for change in free energy for a reaction by looking at delta G of formation of products minus the delta G of formation of reactants. You may have noticed on the little table that I used the other day when we were doing problems with this, that delta G was in a different column. And then the fourth equation deals with entropy. Same equation, it's entropy of the products minus entropy of the reactants. Now you notice that the entropy equation does not have the triangles, because when we don't talk about changes in entropy, we can measure absolute entropy, because the only place it's zero entropy is at 0 degrees Kelvin. So the entropies that you use in this equation are the absolute entropies, and they're on that table as well that we used previously. Remember, the entropy is measured in joules per mole Kelvin. So if you're tying together entropy and enthalpy, they have to be in the same units. The others are all in kilojoules per mole. Kilojoules per mole. There's no Kelvin here because temperature is only part of the entropy factor. All right, so then when I give you some problems to do, you'll use these 4 equations to solve them. Since we're doing this online, we won't get as in-depth with problems as we would if we were in a regular school environment. But at least you'll be exposed to enough to have an idea about this if you run into it in college later on. All right, and that's where I'm going to stop part 3.